Okie dokie. So good morning and good evening, and maybe good afternoon, depending on where you are in the world. My name is Matthias Carlson, and I'll try to just step us through this info session related to the JIP that we're launching now, and that will kick off in Q1 as of or Q4 as of this year. So first of October. We're very excited about launching this joint industry project. Great to also see companies wanting to collaborate through such an initiative like this, and I'm very, very happy to communicate that we have already 3 participating companies, including Cimarex Energy, that I'll talk a little bit more about later. In terms of the agenda for today, or the meeting logistics, we have more than 100 registered participants for this meeting, and we're using something called WebEx event, which makes everybody muted by default, and that's just to avoid too many people talking at the same time. But if you have any questions, just feel free to ask those in the Q&A box, and my colleague Mo will facilitate those questions in the Q&A session. So that's on the right side here in the WebEx event menu. The presentation will be around 45 to 60 minutes, and everything is recorded and will be distributed together with the slides after the presentation. And my goal is not to steal too much of your time today, but just go through a quick introduction to Whitson as a company, do a little bit of a crash course on numerical ray transient analysis, go through the RTA workflow in detail, which is going to be call it the main technical topic covered as a part of the industry project, go through the JIP logistics and details before we have the Q&A session in the end. First, just a short introduction to Whitson as a company. So Whitson was founded by Curtis Hayes Whitson in 1988, and since then we've helped the global oil and gas industry with items related to both on the consultancy side, the software side, and the training side, where the software part is one of the things we've focused on a lot the last year, where we in July of 2020, so just 1 year ago, we launched Whitson Plus, which is a web-based cloud-based system that entails everything that we consider essential for a modern petroleum engineer. So call it the 90+% of the activities that you should be able to perform as a petroleum engineer, while you then seamlessly can export results either into or integrate the more complex systems into Whitson Plus. The Whitson Plus for unconventional reservoirs is essentially designed mainly for tight unconventionals, or so-called shale reservoirs. So basins like the Permian, Eagle Ford, Scoop Stack, Bakken, Duvernay, Montney, you name it. And its intent is to assist in every single key part of the unconventional reservoir workflow, be it PVT and fluids from equations of state, bottom hole pressure calculations, and also the key part of this project, which is the numerical RTA concept. We have also integrated a full physics numerical reservoir simulation module into the tool, which is an equivalent of like an Eclipse or a CMG IMX or a T Navigator type of engine. And of course, you can tie this to forecasting exercises and get DCA parameters and whatnot that has a physical basis. In the modern world, where we see G&A budgets and teams are getting leaner and leaner, it's also a very big focus for us to be able to do this in less than 10 minutes per well. And the key thing that at least we have introduced that is quote unquote a little bit new as of the last year is this numerical RTA concept, and that's the main topic of the joint industry project as well. So when it comes to numerical RTA, the question should be, okay, I've heard about RTA, I never heard about numerical RTA, what is it? And the fundamental piece that I think numerical RTA is very good at, or the vision that it tries to entail, is that it's better to be roughly right than precisely wrong. So with numerical RTA, we're using simplified geometry, symmetry of element models, but full physics reservoir simulation models to handle all the multi-phase flow effects and superposition effects in a consistent manner. So we kind of delegate all that complex math to the simulator. But at the same time, we honor these key RTA concepts, finding estimates of linear flow parameters, A squared of K, and hydrocarbons in place. So in essence, numerical RTA is trying to unite RTA and reservoir simulation concepts. And for those of you who've seen me present before, at least before 2020, RTA and reservoir simulation, at least for many of us, was like pineapples and pizzas, where we enjoy them separately, but only a few of us enjoy the mix. But then Braden Bowie and James Ewart came up with this paper that they presented at UTech last year, where they unite these fundamental RTA concepts that we're very, very familiar with from the industry with the full physics reservoir simulation model that's run in a systematic manner. And I'll go through the details of that RTA workflow outlined by Braden in his paper here in a little bit of a graphical manner through a few slides. I'll then show how that actually looks like in practice through for instance, Whitson Plus, and how we're actually going to look at that particular workflow and try to extend it and look more deep into it through the JIP study that we're launching, and essentially what are we going to investigate or improve upon when it comes to this workflow. So the first thing, just for the results and call it the theory that I'm outlining in this the next few slides, just want to keep that record straight, is that behind the scenes we're assuming a so-called 1D model. So that means that we are using symmetry element of symmetry, and we have no volume beyond the frac tip or above the fracture height. That means that there's only one no-flow boundary in between the fractures, if we like, which also will mean that you go from linear flow to a boundary-dominated system immediately. So very simple from that perspective. That said, we believe that a lot of the concepts that you apply here can also be relevant for more complex geometries. But I just wanted to mention that before we move on. For those of you who are well familiar with RTA and kind of the industry standard workflow, I think this slide right here summarizes that in a nutshell for us with one of my great friends, Dave Anderson, and one of the very good courses at Saga Wisdom, that he summarizes the industry standard workflow, where he combines the so-called square root of time plot with the flow material balance exercise to then come up with a estimate of A squared of K, the so-called linear flow parameter in step 1, and then the hydrocarbons in place comes from step 2. And we all know where the fundamentals from these different plots come from. We know that the square root of time plot, when we're dealing with ideal conditions, a single phase flow, for instance, it could be single phase water or single phase oil above the bubble point, and for instance, constant bottom of pressure. As long as this well or this well is behaving infinite acting, we get a straight or a constant slope on the square root of time plot, as we see on the right here in gray. And from this slope, we can, for instance, try to resolve a square root of K type of parameter or a LFP parameter. What complicates it somehow is that in the real world, we tend to see some effects that is of changing rates and pressure. Typically, we talk about that as superposition effects. Here, we just made a simulated step change in blue, which I think communicates a lot of the complexity that at least I see when I work with clients and look at this particular plot, where you would essentially, due to the superposition effect, get multiple different slopes on the square root of time plot. But the complexities doesn't necessarily stop there, because if you add on another layer on complexity, so here is still single phase, but if we add on the multi-phase flow effect, so the combination of superposition and multi-phase flow effects, then we're getting something that's even more complicated, and that's what Braden is describing in his paper together with James. And I think these two call it cartoons that are, or not cartoons, the simulation results that are based on the model that I just showed on the last plot, where you have an infinite acting model, but it's controlled on two different drawdown profiles, one going below the saturation pressure at around 300 days, the other around 150 days. And if we superpose the square root of time plot on this particular figure, we actually see a slope change as we drop below the saturation pressure, which are due to this combination of multi-phase flow effects and superposition effects. And if we misinterpret this to be boundary effects, for instance, if we, for instance, pick time to end of linear flow based on these observations, we tend to end up with higher permeability estimates, shorter fracture half lengths, justifying more wells per section, which just speaks to this saga that we've heard about in the industry the last 4 or 5 years with respect to overcapitalization. So the solution to this, quote unquote, is the so-called Bowie workflow that has nothing to do with David Bowie, but it's just based on the paper by Braden that was presented last year, where the following two definitions are very key for the workflow. If you understand these two call it definitions and their fundamental impact on just well performance for tight unconventionals, you actually understand and you can recreate this entire workflow yourself in Excel or whatnot. We made one little modification on it, so we've actually written a paper together with Braden the last 6 months that will be presented at ATCE, just to make it a little bit more generalized, where we include the square root of porosity in this term right here, and we'll get back to why we decided to do that. But with these two definitions, which are well-established definitions in the literature, we can come up with the following three observations if we run, it could be a simulation model, for instance, which was how I guess Braden observed it initially. So for any two wells with the same value of LFP square root of porosity, the rate performance is identical during infinite acting behavior. With the same ratio of LFP to OIP, all the relative rates, so the GOR and water cuts, will be identical for all times. That's both infinite acting and boundary dominated. So remember what the fundamental model is in this case. And if both the LFP value and OIP value is the same, then the rate performance will be identical for all times, both infinite acting and boundary dominated. And these cases, they assume, of course, a given fluid incisation, a relative permeability set, and the same bottom hole pressure versus time. And the question that comes up is like, okay, what two wells actually has all of these three same assumptions? Well, the nice thing here is that we're actually utilizing these relationships on the same well. So, and for a given well, it might be uncertain, but a given well should have one fluid incisation, a more representative rel perm set, and a set of bottom hole pressures versus time. To remind ourselves that these things are true, here we just remind ourselves that as long as the LFP square root of porosity is the same, no matter how you come up with this product for your model, you get exactly the same behavior during infinite acting time. If we look at the case where we have an LFP and OIP ratio that is the same between three different cases, all the relative rates are the same, here just displayed as GOR. And we also see one other fundamental thing is just that the absolute rates, or the absolute well performance rates, are just a multiplier of each other. So if we multiply all this or scale these up to the same level in terms of both OIP and LFP, we actually end up with three cases that are identical, even though the XF changed, the length of the well changes, the number of fractures, the permeabilities, et cetera, et cetera. And with these three fundamental relationships, Braden came up with this workflow together with James, and there was also a lot of other people on that list in terms of sparring partners, and through some work that they did there for a couple of years at Apache. So I'll just go through this workflow that's 100% automated in Whitson Plus. Everything is done in the cloud, so when you run the workflow, it leverages, it essentially parallelizes, I think, around 12 different reservoir simulation models to create the type curves that are key for the workflow. The first step of the Bowie workflow, if you wanted to do it yourself, is to create a numerical model that's large enough to always behave infinite acting. So you're essentially forcing a flow regime upon your simulation model. How would you do that? Well, it's trial and error. The easiest way to do it is to create a symmetry of element model where you have a very far or a far distance to the closest boundary, and you just take this particular model that you've defined. So you know the permeability of this model, you know the porosity of this model, the height, the XF, etc. So that's a known parameter for you because you made the model. And then you run this infinite acting model on the well's actual measured bottom hole pressure versus time. Okay, so then you get a set of model rates that are, call it quote unquote, infinite acting model rates. Step 3 is very simple. You take the actual rates measured in the field divided by these infinite acting model rates. You get a ratio over time. This ratio over time is then multiplied with the known LFP square root of porosity in step number 1, and you get the key diagnostic plot in the workflow, which is this instantaneous LFP plot, or the Bowie plot as we call it internally. And from this key diagnostic plot, you can make the flat horizontal line indicates infinite acting linear flow. Deviation below this line represents boundary dominated transitional flow, depending on what your underlying geometry is. And the magnitude of the flat line indicates the LFP square root of porosity. Then the only last thing you need to do is to run the model you define in step number 1 in a systematic, but just reducing the tank sizes. What we mean by that is that we reduce the distance to the closest boundary. You do that in a systematic manner, you'll get models that transition into boundary dominated flow sooner and sooner and sooner. And you then get a wide range of type curves that is each associated with an LFP-OIP ratio. From the actual measured data that you have, you can then pick an LFP value that you think is representative. We'll look at an example now in a second. And then you overlay all the type curves, pick the type curve that is closest to your observed data. And what you end up doing is actually then you pick an LFP, you pick a type curve which has an associated OIP, and you're done. So you've done the 2 exercises that you need to do, LFP and OIP. If you look at it a little bit more holistically, how you would do it in a software, of course, the method, as most other reservoir engineering methods, assume a fluid initialization and a rel perm set. So you need to define that on the front end of the exercise. And then you do the interpretation, and in the interpretation, you're just picking an LFP and an OIP. And some people like to actually stop here. They say, I don't know what the XF is, I don't know what the perm is, the height, etc. So they just want to use that and correlate that to completion parameters. Some people would like to take it a step forward and get some realizations in terms of history matches, for instance. So if you do that, you can resolve your XF and K as a last step. And kind of the umbrella of all these 3 steps is what we call numerical RTA in Whitson Plus, and is also what we're going to look at in detail in the joint industry project. Of course, these things, since we're already using a full physics reservoir simulation model, we can use that consistently in a numerical reservoir simulation exercise. And the nice thing is that if you've done a good job in the RTA part of it, and you export those parameters into the history matching exercise, you'll get a very, very good fit on the first run, which at least for me and my colleagues like Mo and others that's been doing these exercises a lot through a lot of, call it unsystematic history matching, it is really a kick with the first time you do it. Just to connect the dots a little bit, what you just saw might seem a little bit foreign, maybe a few new concepts and plot, but fundamentally it's what we've always done. We use fundamental RTA concepts just from analytical RTA. So back to Dave right here, we use the square root of time plot to get the LFP square root of porosity, and we use some kind of flow and material balance exercise to come up with the estimate of OIP. Okay, and here again, from the slope of this equation right here, you can also see that this is essentially LFP square root of porosity, while all these other parameters here are for all practical purposes PVT properties, if we ignore the rock compressibility term in CT, which are inputs into the analysis. Okay, so it is actually very familiar to all of us. So now we're going to go through a little demo of just how this would work in practice in Whitson Plus. Here you see the numerical RTA feature here to the left, and as I mentioned, the numerical RTA module would require a fluid initialization, so a GOR, water saturation, initial pressure, etc. And of course, a set of matrix permeabilities. Okay, so here we just use something close to default queries. You run this case, and then in the step 2, where you actually do your interpretation, that's where you would actually do the interpretation in terms of LFP and OIP. Here I've already, so I'm using a synthetic case to illustrate, and we'll take a look at a real field case in a little bit. But fundamentally here at this step, I only have one job as an engineer. I need to pick an LFP. So if I pick this at 80,000, for instance, I see that I'm under predicting my curve right here. And I can also look at different types of diagnostic plots. It could be the Cume plots or the oil rate plots to see all the time if I'm on par or not. Same with GOR, very fundamental exercise or very fundamental property that you can look at over time to analyze whether you're doing a good job or not. And as we know, GOR and well performance or producing GOR and well performance are tightly coupled in terms of flow regimes and whatnot. If I do this exercise correctly, here I know the answer. So I know that the LFP is around 100,000. I know that the closest OIP stem is around 331. So I can just click this OIP and you'll see it will then appear right here. So I click it, it updates automatically. And then if I want to, I can just make sure that I either remove that particular stem, or I can do the opposite, where I just want to keep that particular stem in all the different plots and look how the fit is. And as this is a synthetic case, so we know that's doing a very good job in all the plots. And then I can move on to the last step, where I've already picked an LFP and OIP, and then I can input my estimates of matrix porosity, reservoir height, well lateral length, and number of fractures. That will resolve a matrix permeability and reservoir or fracture half length that I can then decide if I want to use in history matching. Okay, so if I decide on doing that, go into history matching, and we see I get a pretty good fit on my first run. This is indeed perfect. The grid refinement is the same. Everything is the same. So that makes a lot of sense. If we wanted to do this with a field case, it becomes a little bit more complicated, and it's also why we want to do this particular JIP. This is from the SB public data repository. Here you can see one of the investigation items in the JIP is how to consistently in the workflow deal with injected water. Typically very hard with unless you do something with the water saturation close to the fracture phase, etc., to deal with the early time water, but it definitely has an impact on the analysis. Of course, the data quality, etc., of the data you have will have an impact on the analysis. And on purpose, I wanted to just show how complicated it can be with some bad data for a case right here, where mainly the key plot, the Bowie diagnostic plot, is a little bit maybe hard to conclude on whether this is a good fit or not. But we see 60,000, and maybe this OIP stem right here, that's a decent job. If I want to make sure that my cumes are okay in place, I see at the end of history here, okay, we're close. Maybe I can work here and make it even more perfect if I want to spend some more time here. But if I'm in a rush and I want to get some realizations that I think make sense, I can input some last parameters and export this into the history match. And on the first run, get a pretty decent match. Here I just control it on oil rate control, a little bit off on gas, but for all practical purposes, decent, at least to be done so quickly. So back to the presentation and more on the practical aspects of the JIP. The key summary of the JIP itself is that it's a 1-year JIP. So it's going to last from 1st of October 2021 to then the fourth quarter or beginning of fourth quarter 2022. The nice thing is that everybody that joins the JIP, they'll be given full access to Whitson Plus, the software platform that you just saw, which has a lot of other things than just pure numerical RTA. It has bottom hole pressures, decline curve analysis, PVT from equations of state, and thermodynamic engines and whatnot. We'll do a proof of concept of the methodology on 10 wells that the company wants to analyze. This can be tricky wells from both fluid perspective and also to explain from a well performance perspective. And one thing that we got when we wanted to kind of assign this RTA JIP was to a lot of feedback that we got was to have technical knowledge sharing sessions with all the members at once. That means that we're not going to share any data between the operating partners in terms of production data and well performance data, but it's going to be more on base cases and reference cases in different basins. Where do we see it works well? What problems do we have? What problems do we need to solve to improve upon the workflow? And how does this workflow compare to other methods? And how sensitive is it to different types of assumptions? And the participation fee is $30,000 per company, flat, and all the participants get access to the same data that I'll go through in a second. In terms of the investigation goals, we'll focus a lot on develop best practices and guidelines related to the methodology. We'll use field data to perform several proof of concept studies in different unconventional basins. So that can be, either of the North American ones, it can be some of the ones in the Middle East, or in South America for that matter. The nice thing about using real data is that then we are actually exposed to the real problems. So if we're not able to explain what we observe in the field, and if the model is not working well for that, then there's a red flag already there. So we need to be able to solve that consistently. There's at least when we've worked on the workflow with multiple operators the last 6 months, we have identified questions that typically come up with regards to the workflow. How is it impacted by well interference and multiple wells in the pad? How is it impacted by non-ideal well geometry? So like EFR type of models, volume beyond the frac tip, volume beyond the frac height, if it's subject to differential depletion, and also relative permeability assumptions, which Hamid Bemanesh at Saga and also Clarkson has done some great work on. If possible, generalize this workflow to consistently account for completion water. That's something we just saw in the field example, and it's you can do it in like a history matching exercise where you tweak something, or you can manually go in and input a higher water saturation closer to the hydraulic fracture just to make sure you match the water cut. But how do you do it consistently in the workflow? That is not solved as of today. If any of you have any good suggestions, I would love to hear it. Not to mention compare the method to just with real field data, but compare it to analytical methods, and also compare it to other multi-phase flowing material balance exercises that has been proposed in the industry. The timeline is very simple. The startup is Q4 as of this year. That's when we started up and provided data. Then the project period is 1 year with frequent update meetings, and then there's going to be a short course and final delivery with a final presentation at the end of the project. And in the project period, there's going to be 2 knowledge sharing sessions among the GIP participating members, where we will try to facilitate some interesting discussion on the observation of this workflow, but also how it compares to other workflows that exists in the industry and other methodologies that is out there, to keep it real and keep it honest. The knowledge sharing sessions is an arena for sparring and discussion related to unconventional well performance in general. So that's very, very important to emphasize that when it comes to the knowledge sharing sessions, it's not only a focus related to the numerical RTA workflow. So that brings us to point number 2, that the focus of these sessions are also beyond the numerical RTA workflow. We're going to compare different methodologies and assumptions, and it's going to be relevant because we're going to use just real field data, and it's going to be consistent because we all will have access to the same tool. So things like, things like gridding, the numerical models, thermodynamic engines, and all these things that typically leads to inconsistencies when you compare one software product to another will not be an issue in this context. So the question is, what is it in it for the participants? And that's a great question. First of all, You get full access to all the modules in Whitson Plus during the project period. You get the proof of concept of these 10 wells that you pick to provide to the study. You get a JIP report and associated presentations with key takeaways. Participate in these technical knowledge sharing sessions. Of course, have on-demand work sessions with people at Whitson for sparring, support, and training. Preferential pricing on future software subscriptions, and the one-day course at the project end, which we'll hold in Houston at our offices there, but it will be also possible to join those virtually for those who don't want to travel down to Houston. The last slide is related to confidentiality and other remarks. So the data provided by one company will not be shared with other companies in the JIP. And the only information shared with all the participating companies is general conclusions and experiences from the work performed during the JIP. No data of the results from the study will be published without written consent of the JIP participants. So when it comes to like the information that could be shared, like we're not sharing specific data points and whatnot, but Braden the last 6 months, he found out a very, very consistent way to deal with how can you actually input a low fracture conductivity into the workflow and use it consistently, and when you also export out to the history matching module. And that can be a good example of an output from the study that's not, call it field data specific or related, but it's more a general takeaway that will be a nice takeaway from the study. So the same goes for if we find a consistent way to deal with the injected water in the workflow. So that was everything that I wanted to go through. I think in terms of time, we were about 36 or 30 minutes. So that's good time, I think. I don't know if there's any questions. Let's see. One question that came in is that, or the question related to whether or not we share the slides after the presentation. The answer to that is yes, as I mentioned. We'll also share the recording of the presentation, so that will all be distributed to the different participants in this call. Other questions than that? Let's see here, Q&A. Yeah, so I see there's do you have any questions there, Mo? Or yeah, one. For some reason I can't open this thing here, but the question is: are you assuming a planar fracture per individual cluster or per stage? So that's actually a good question. So the question is: are you assuming a planar fracture per individual cluster or per stage? So when you're doing the RTA workflow, you're just resolving the A squared of K parameter, the linear flow parameter. So how you would like to distribute that area in terms of number of fractures, whether that assumption is per stage or per cluster, that's actually something up to you as a user when you go into the last stage of the workflow. And just to make that a little bit less abstract, in this last stage right here, let's say for sake of argument, you have 100 stages. Maybe that's a lot. Let's say you have 50 stages in the well. Then if your assumption is that you have 50 stages in that well, then you get a matrix permeability in this case of 2000 nanodarcy. If you then assume that it's 4 clusters per stage and all of them generate a fracture, you're reducing your matrix permeability in this case to 140. So that's something you as a user will decide, while the numerical RTA workflow provides you with the LFP square root of porosity parameter and the OYP estimate. So that you can play with as much as you like. And the fundamental theory is actually, as long as the LFP number is the same, the OYP is the same, if you export that into a realization, you should get the exact same number every single time, as long as the matrix permeability and fracture half-lengths resolved consistently. So yeah, will these models be compared to other similar modeling softwares? That is a great question as well. These models, the way we think about it is, if you want to improve a space in terms of what's there currently, it's very, very helpful to also compare it to other modeling softwares as well, and other workflows too. So that's something we definitely welcome and that we think should be a part of these knowledge sharing sessions for sure. And there's also a lot of companies that have internal made workflows that are either just because they're developed internally, nobody else has access to it, or there might even be confidential. So for those, we can also make comparisons to those methods as well. Yeah. So the question, another question is, can you use this workflow for any fluid type or only oil wells? So that's a good question. So related to the original paper was mainly written for oil wells. And what we've done in the updating paper that's going to be presented at ATCE now in September, we've actually generalized the workflow for all fluid systems. So that's including all the, not only oils, but near critical systems, even two-phase saturated systems. So if you have a dual PVT system, near critical gas condensates, wet gases, and dry gases. So that's one of the key things, I guess, that we've updated in that paper. So that's going to be available for I guess download on one Petro at that point, and we probably can distribute it then. But it's yeah, it's essentially this paper right here. Let's be 205884. So it's just called Numerical RTA and Tight Unconventionals. Braden is one of the co-authors, and a lot of my other colleagues at Whitson just explaining these different add-ons to the methodology. A lot of the stuff we actually talked about in this call. To very easily generalize it to all fluid systems, we just use a total formation volume factor instead of the oil formation volume factor. The nice thing about that is that when the oil saturation initially is 100%, then it will simplify to BO, but for two-phase saturated systems and gas condensates, it will then account for all the complexities associated to that. So it's exactly the same numbers you have to pick no matter what fluid system you're dealing with. So I hope that, yeah. Yeah, very good. Yeah, another question that comes up here on my side is how sensitive is the relative perm on the interpretation? Of course, relative permeability is an input to the analysis and will be impacted like any other types of any reservoir simulation model that you run will have an assumption of relative permeability sets. So it's in the same way this workflow is sensitive to that. Hamid Bemanesh, that was in Clarkson's group, I think he's also associated with them still, and also is with Saga Wisdom. He actually did some great work on how sensitive rel perm assumptions is for this method, and it could be up to I think, if I remember correctly, 2x difference in OIP estimate. So it was for the LFP parameter, it had essentially no impact in terms of at least when you pick it in terms of engineering accuracy. But when it comes to the OIP estimate, or the hydrocarbon in place estimate, it has a larger impact. Do you have intentions to add abilities to the software, such as production beyond the fracture tips, both fracture height and XF, and variable saturations to better handle injection volumes? That's also a very good question. So the software already handles volume beyond the frac tips and whatnot, so you can increase the fracture height and also call it the half length of the reservoir that you can do already if you like. Call it having different saturations in the model. So right now that's not something we accommodate, but I think that's along the direction that's needed to be included to at least consistently account for injected water. So I think that's a very good suggestion. Yeah, that is very good. And for those of you who've asked the questions related to the FCD, like how we use FCD or consistently in the workflow, you can go into our manual.whitson.com, go into numerical RTA, and there's a section on the bottom there related to how finite connectivity fractures are included in the workflow, and that's also summarized in the ATCE paper that will come out next month. Yeah, the deadline for the participation of the deadline is Q4 as of this year, so 1st of October. But we're going to keep, so I guess the strict deadline will be end of the year. So we take participations all the way from now, essentially, all the way to 31st of December as of this year. So it allows for some time for the companies to think. And as I mentioned, we already have 3 companies participating. So it's, and I always say that when we launch a JIP, as long as one company is in there, we'll conduct the JIP, and now we're 3, so that's a good start. And of course, we welcome all the companies that would like to be a part of this for the technical discussion using real data as well. I think that's something, at least I personally have missed a little bit, especially the last year now with COVID and whatnot. So it would be great to meet and discuss with industry participants again. Last question that I think is related to the gridding. So like any full physics reservoir simulation exercise or any numerical model is dependent on grid refinement, and of course that's also an input to the analysis. What's nice is that since you're using the same gridding in the RTA piece as what you do when you export it into a higher order type of analysis, such as history matching, at least from the gridding perspective, it's consistent. Whether it's 100% accurate or not, if it's enough highly gridded, etc. Sometimes that can be debatable, but at least it's 100% consistent, so you get consistent results. So you don't have to change stuff when you go into the history matching exercise. Yeah, have you tried the workflow for studying multiple wells at the same time? The answer to that is yes. So if you analyze multiple wells at the same time in a pad, for instance, then you, at least what we did, and I think what Braden has done, is that you aggregate all the LFPs and OIPs for that particular pad. You then look at that pad, call it as a composite LFP and OIP number, and you compare it to other types of developments, and you ultimately tie this to economics. So that's how that is solved, and is also one of the investigation items in the JIP. So how will well interference, parent-child effect, etc., impact our linear flow parameters and hydrocarbons in place? Very good. So I think if there's any other questions, you can just write them to us as a follow-up to this meeting. We first of all thank everybody for joining this call. We'll send out the slides and recording later today or tomorrow, and we wish everybody a still good Tuesday.